Welcome. We are studying our fifth chapter, multiple integrals. Today we shall start our third module, Green's theorem. In this module, we shall study Green's theorem, its proof and its consequences. We start our study with discussing certain types of curves in Rn, especially in R2. First, closed curve. A curve gamma from bounded closed interval AB to Rn is said to be a closed curve in Rn if and only if its initial and terminal points coincide, that is gamma A and gamma B are identical. Next, simple curve. A curve gamma from the interval with endpoints AB to Rn is said to be a simple curve in Rn if and only if gamma is 1 to 1 in the semi-open interval open A closed B. This means if T1 and T2 are 2 points in the interval with endpoints A and B, at the side A it is open and T1 is different from T2, then gamma T1 is different from gamma T2. Equivalently, we can consider the interval as closed A open B. Simple closed curve. A curve gamma from AB to Rn is said to be a simple closed curve if and only if gamma is both simple and closed. That is, for different T1 and T2 from the domain, we must have gamma T1 and gamma T2 are different, and secondly, gamma A must be equal with gamma B. Next, rectifiable curve. A curve gamma from AB to Rn is said to be a rectifiable curve if and only if it is a piecewise smooth curve and has a finite length. Finally, Jorda curve. This is more important for us. By a Jorda curve gamma from AB to R2, so here the codomain is the Euclidean plane, we mean a simple closed curve. Jorda curve theorem. Every Jorda curve C decomposes the plane in which it is contained into two disjoint open connected sets. Both these sets have the curve C as their common boundary. Looking at the adjacent picture, we can easily understand this. The region which is bounded by the curve C is called the interior of C and is denoted by the symbol interior C. The other part which is unbounded but has C as its boundary is called the exterior of C and it is denoted by the symbol exterior C. We should be careful that interior C, exterior C as mentioned above are different from the topological notions of interior and exterior of a set in a topological space. Moreover, here C denotes a continuous map, not a set. If we consider the trace of the curve C, then its topological interior is the null set, because here we are considering the Euclidean topology over R2. Actually, a Jorda curve partitions the plane into three connected sets. First one, a domain bounded by the curve C, that is interior C. Next, an unbounded domain which has C as its boundary, that is exterior C. And thirdly, the trace of the curve C. Among these three, the first two sets are open, but not the third one. We can attribute a notion of direction or orientation to a Jorda curve. Let C be a Jorda curve. If a point moves along C in such a manner that interior C is always at its left, then we say that the curve is traversed in the counterclockwise direction or anticlockwise direction or positive direction. The other direction is called the clockwise direction or negative direction. Let us look at the adjacent picture. We considered an annular region. If we consider the curve which is bigger, then we can see for its positive direction is marked here, and for the inner curve we have also marked the positive direction. In the remaining part of this chapter, we shall use the symbol oriented integration to denote line integral along a closed curve in the positive direction. If C is the corresponding closed curve, we shall denote this by this symbol. Now, we shall recapitulate a result we studied in the third module of the previous chapter, that is line integrals. Let gamma from AB to R2 be a piecewise smooth curve. A is an open set in R2 containing the trace of gamma, and F from A to R2 be a vector field. Now, we express both F and gamma in terms of their component functions, that is, let F equal to F1 F2 and gamma equal to gamma 1 gamma 2. Then for every t from the closed interval a b, we find that inner product of f gamma t and gamma dash t equals with inner product of f1 gamma t f2 gamma t with gamma 1 dash t gamma 2 dash t. So, this equals f1 xy x dash t plus f2 xy y dash t, where x equal to gamma 1 and y equal to gamma 2. Consequently, the line integral of f with respect to gamma, that is integral a to b f d gamma, equals integral a to b f1 xy x dash t dt plus a to b f2 xy y dash t dt, which equals with a to b f1 xy dx plus integral a to b f2 xy dy. Let C be a piecewise smooth Jordan curve and R be the region bounded by C. That is, we assume R equal to interior of C union trace of C. In other words, C is the boundary of R. Next, let A be any open set in R2 containing R, and F from A to R2 be a continuously differentiable vector field. The components of F are F1, F2. So, F1 and F2 are two differentiable scalar fields defined on the set A. First, we assume that the curve C is such that every vertical line and every horizontal line segment intersects C at most twice. Let us look at the adjacent picture. We drawn such a curve. Then we can find points A, B, D, E, C on this curve, which are nearest and farthest from the coordinate axis. That is, A is nearest from y axis, B is farthest, and from the x axis D is nearest and E is farthest. Now, we can say that the portions curve ADB and curve BEA together construct the curve C. We note that every vertical line intersects curve ADB at most once. The case is similar for the curve BEA. Let us denote these two curves by y equal to gamma 1 x for curve ADB and y equal to gamma 2 x for AEB for every x in AB, where A and B are suitably chosen. Here curve ADB indicates the only curve in our consideration on which the point A, D, B lie and so on. Now, line integral of f along C is given by integral inner product f c t c dash t dt. This equals with integral over C f1 dx plus integral over C f2 dy. Then line integral of f1 over C dx equals with integral over curve ADB f1 dx plus integral over BEA f1 dx. Now, the value of integral of f1 over dx for the curve AEB is the negative of the same integral, but the considered curve is BEA. So, this equals with a to b f1 x gamma 1 x dx minus integral a to b f1 x gamma 2 x dx. So, we can write this as integral a to b f1 x gamma 1 x minus f1 x gamma 2 x dx. Since on the curve ADB xy equal to x gamma 1 and on the curve AEB xy equal to x gamma 2. On the other hand, double integral over the region R del f1 del y dx dy equals integral x equal to a to b integral y equal to gamma 1 x to gamma 2 x del f1 del y dy dx. So, this equals with integral x equal to a to b. Here the integrand is f1 xy, where the lower limit is y equal to gamma 1 x and upper is y equal to gamma 2 x dx. So, this equals with integral from a to b f1 x gamma 2 x dx minus integral x equal to a to b f1 x gamma 1 x dx. Now, combining 1 and 2, we find that integral over c f1 dx equals double integral over r del f1 del y dx dy. On the other hand, we can consider the same curve C as the join of the portions EAD and curve DBE. Like the previous case, here also we note that every horizontal line intersects curve EAD or curve DBE at most once. Let these two curves be represented by the equations x equal to phi 1 y for curve DAE and x equal to phi 2 y for curve DBE for every y in bounded closed interval with endpoints C and D. Here C and D are suitably chosen. Proceeding as above, we find that line integral of f2 dy over C equals with line integral of f2 dy first over curve DBE then over curve EAD, and integral over curve EAD equals with negative of integral over DAE. So, this equals with integral C to D f2 phi 2 y y minus f2 phi 1 y y dy. Moreover, double integral over r del f2 del x dx dy equals y equal to C to D integral x equal to phi 1 y to phi 2 y del f2 del x dx dy. So, this equals with integral equal to C to D f2 phi 2 y y minus f2 phi 1 y y dy. Combining 4 and 5, we find that integral over C f2 dy equals with double integral over r del f2 del x dx dy. We combining 3 and 6 and we find that line integral of f over C equals with integral over C f1 dx plus integral over C f2 dy, and this equals with minus integral over r del f1 del y dx dy plus double integral over r del f2 del x dx dy. We write f1 equal to m and f2 equal to n. Then the above relation transforms to line integral over C m dx plus n dy equals double integral over the region r del n del x minus del m del y dx dy. Now, we consider another curve. We assume that the region R is bounded by the lines x equal to a, x equal to b. These are two vertical line segments and two piecewise smooth curves gamma 1, gamma 2 from AB toward satisfying gamma 1 x lesser or equal to gamma 2 x for every x in AB. Then the boundary of R, that is del R, which is C, is the join of the curves given by C equal to curve ABE plus line segment EFG plus curve GHI plus line segment IJA, as shown in the adjacent figure. Clearly, C consists of the graph of y equal to gamma 1 x, then a vertical line segment EFG, then the graph of y equal to gamma 2 x in the opposite direction, and ended by another vertical line segment IJA. Here, line segment EFG denotes the line segment with endpoints E and G, where F is an intermediate point and so on. We can easily understand that the previous region which we discussed earlier is a special case of this one, where the vertical line segments reduces to 2 points. Comparing with the previous discussion, we find that first, there would be no change for double integral over the region R. Next, for the line integral, we have to consider integral over line segment IA of F1 and integral over line segment EG for F1, but there is no such line integral for F2, because if we consider these two line segments, over them there is no change in the variable x. So, the corresponding two line integrals reduce to 0, thus we have the same result as before. Next, we assume another kind of region. We have shown such a region in this figure. We assume that the region R is bounded by the lines y is equal to C, y is equal to D. These are two horizontal line segments, and the curves phi 1, phi 2 from CD to R satisfying phi 1 y lesser or equal to phi 2 y for every y in CD. So, clearly the points on phi 1 will be always to the left of phi 2. Now, the boundary of R, that is del R equal to C, is the join of the curves given by C equal to line segment ABE, then curve EFG, then line segment JHI, and finally curve IJA. Clearly, C is composed of a horizontal line segment ABE, then the graph of x equal to phi 2 y, followed by another horizontal line segment, and finally the graph of x equal to phi 1 y in the opposite direction. This case also can be similarly treated resulting in the same equation. Next, we suppose that the piecewise smooth Jordan curve under consideration is not of the above three cases discussed. So, gradually we are proceeding towards complicated type of curves, but here we consider a simple one. Let us consider a curve C as shown in the figure. We choose 2 points S and T on the curve C such that the line segment ST or a simple curve joining S and T and lying within the interior of C divides interior of C into 2 regions of any types we considered earlier. Here we have integral over the curve ABSTA of mdx plus ndy equals integral over the region R1 del n del x minus del m del y dx dy, and integral over the curve dETSD mdx plus ndy equals double integral over the region R2 del n del x minus del m del y dx dy, where interior of C is R, interior of the curve ABSTA, which is a closed curve, is R1, and interior of the curve dETSD is R2. We add the two results and find integral over R del n del x minus del m del y dx dy equals, the integrand remains same, double integral over R1 plus double integral over R2. Here we put the values. So, this is integral over the curve ABSTA plus integral over the curve dETSD of mdx plus ndy. Now, ABSTA and dETSD, both the curves can be expressed as join of some other curves. So, we express integral of mdx plus ndy first over curve ABS, then line or curve ST, then TA, then DET, then TS, and finally SD. Now, the integrals over ST and TS cancel each other. So, finally, we are left with integration of mdx plus ndy over ABS, then STD, then TA. So, that is integral over C mdx plus ndy. Such curves ST are called auxiliary curves. For complicated regions, we take the help of more than one auxiliary curves. However, this result can be proved for any region bounded by a piecewise smooth Jordan curve. So, now we are in a position to state Green's theorem, which reads as follows. Let C be a piecewise smooth Jordan curve and R denote the region bounded by C along with the trace of C. Let capital A be an open set in R2 containing the region R and capital F from A to R2 be continuously differentiable. If M and N are the components of F, then integral over C m dx plus n dy equal to double integral over R del n del x minus del m del y dx dy. Now, we consider the formula used in Green's theorem, that is integral over C m dx plus n dy equal to double integral over the region R del n del x minus del m del y dx dy. In this, we first put m equal to 0, that is the 0 scalar field defined over the same domain. Then from the above expression we have integral over C n dy equal to double integral over the region R del n del x dx dy. Similarly, considering capital N to be the 0 scalar field, we find line integral over C m dx equals to minus double integral over the region R del m del y dx dy. So, from Green's theorem we get these two relations. On the other hand, if we add these two relations, we can find the relation used in Green's theorem. Thus, we have another alternative expression for Green's theorem. Let C be a piecewise smooth Jordan curve and R denote the region bounded by C along with the trace of C. Let capital A be an open set in R2 containing the region R and capital A from A to R2 be a continuously differentiable vector field. If M and N are the components of F, then integral over C m dx equals minus double integral over R del m del y dx dy and line integral over C n dy equals double integral over region R del n del x dx dy. It is evident that Green's theorem establishes a relationship between the line integral along a simple closed piecewise smooth curve C, that is a Jordan curve C, and the double integral over the plane region D bounded by C. In the year 1846, Cauchy named this theorem after George Green. So far, we have stated Green's theorem and proved it for simpler types of curves. Let us now recall the fundamental theorems for line integrals. We found that for a gradient scalar field f, we can know the line integral of f over a curve by knowing the values of f at its endpoints. So, Green's theorem is the two-dimensional analog of this result. Here we can know the integral over a region by knowing the line integral over its boundary. Using Green's theorem, we can evaluate double integrals by line integral. An easy but useful application of this is to calculate the area bounded by a Jordan curve. Let R be a region where its boundary delta R is a Jordan curve. Then the area of R is given by the following. We know area of R equals integral over R dx dy. So, we can write this as double integral over R del n del x minus del m del y dx dy, provided we can find a vector field f with components m n which is smooth and satisfies the condition del n del x minus del m del y identically 1 over the region R. Let us consider the scalar fields m and n defined over the region R as follows. Say nxy is given by xy plus x and mxy is half y square. We can check that it is smooth and it satisfies the required condition. So, we have area of R equal to line integral over delta R half y square dx plus line integral over delta R xy plus x dy. Another choice for n and m would be easier to deal with. if we take nxy is identically half x and mxy is identically half y with a negative sign. In this case, we find that the area of R is double integral over R dx dy is equal to half integral over delta R minus y dx plus x dy. If we express delta R in a parametric form, that is, say x equal to xt, y equal to yt, where the domain for the parameter is bounded closed interval a b, then area of R we can check that it is half integral a to b determinant xt yt x dash t y dash t dt. Now, we cite an example here. Let R be a bounded region in R2 whose boundary delta R is a piecewise smooth Jordan curve. Let Fg be two scalar fields defined and continuously differentiable up to second order on an open set containing R. Then line integral over delta R Fg dx plus dy equal to double integral over R g del f del x minus del f del y plus f del g del x minus del g del y dx dy. So, in the left hand, if we compare with the term m dx plus n dy, we can check both m and n are equal to Fg. So, writing this, we can get the desired result. The case is similar for the second one, which we have shown in this slide. So, we have proved the results. Next, we shall consider geometric interpretation of this result. Let gamma from AB to R2 be a piecewise smooth Jordan curve with gamma dash be continuously differentiable. We have already studied that the arc length function s of gamma is given by st equal to integral from a to t norm of gamma dash u du, where t comes from a to b. Then capital Ts equal to d gamma ds gives the unit tangent vector to the curve gamma. Let f equal to mn be a continuously differentiable vector field defined on an open set containing the trace of gamma. We also define a scalar field phi on the trace of gamma by phi of gamma t defined by inner product f gamma t capital T. Then we can check that inner product f gamma t gamma dash t equals with s dash t phi gamma t. Consequently, line integral over gamma phi ds equals to line integral over gamma f t ds. If we express gamma t equal to ordered pair x t y t, then gamma dash t equal to x dash t y dash t. Hence, inner product f t equals to inner product of m n and x dash t y dash t. So, this equals m x dash t plus n y dash t. So, from the above we find that line integral over gamma m dx plus n dy equals to integral over gamma inner product f t ds. Next, let mu t be the vector formed by rotating the vector t t equal to x dash t y dash t through an angle pi by 2 in the positive direction. Then we have mu t equal to y dash t minus x dash t. For every suitable t, one can verify this. If gamma dash t equal to x dash t y dash t is different from the 0 vector, then obviously mu t is also different from 0 vector. We can define n t equal to mu t by norm mu t, that is 1 by norm gamma dash t mu t for every suitable t. Clearly, n t is a unit vector. We call this the outward normal vector to gamma at the point t. In the adjacent picture, we have shown on a curve gamma at two distinct points the unit tangent vector capital T and the unit outward normal small n. Now, inner product f n equals with inner product of m n with x dash t y dash t. So, this equals with m y dash t minus n x dash t. That means integral over gamma minus n dx plus m dy equals to integral over gamma inner product f n ds. Now we discuss Laplacian of a scalar field. Let phi be a scalar field defined on a subset of R2. The Laplacian of phi is defined by nabla square phi and is defined by nabla square phi equal to del 2 phi del x2 plus del 2 phi del y2. A scalar field f is said to be harmonic on a region R if and only if everywhere on R nabla square f is identically 0. Let f be a differentiable scalar field. For any vector v, the vector derivative of f at the point A with respect to a vector v is given by the following: vector derivative f dash a v equals to summation over I vi del f del xi at the point A, that is inner product of the vectors v and grad f at the point A. In short, we express these as del f del v equal to inner product of grad f and v. Now, let C be a piecewise smooth Jordan curve. For any vector field f equal to mn continuously differentiable over a set containing the trace of C, we have already deduced that integral over C m dx plus n dy equal to integral over C inner product f t ds and integral over C minus m dx plus m dy equals to integral over C inner product f n ds, where t and small n denote respectively the unit tangent and unit normal vector over C. Now, let f and g be two vector scalar fields having continuous partial derivatives at least up to second order over an open set containing a region R. We further assume that the region R is such that the boundary delta R of R is a piecewise smooth curve. Then integral over delta R del f del n ds, this equals with line integral over delta R inner product grad f n ds. Putting the values, we find that after a little calculation that equals with double integral over the region R nabla square f dx dy. Using this, we also find that f nabla square g plus inner product of nabla f nabla g, after a little calculation it equals to del del x of f del g del x plus del del y of f del g del y. Now, using Green's theorem, we find that double integral over R f nabla square g plus inner product grad f grad g dx dy equals to line integral over delta R f del g del n ds. Using the above result, we further notice that integral over delta R f del g del n minus g del f del n ds equals to double integral over R f nabla square g minus g nabla square f dx dy. Now, we state Green's formula. In case both f and g are harmonic, that is nabla square f and nabla square g are 0, from the above we find that integral over delta R f del g del n minus g del f del n ds equal to 0. This result is known as Green's formula. Now, we discuss some topological concepts. Simply connected domain. We consider the Euclidean plane, that is the set R2 equipped with its usual topology. Let D be a non-empty connected open set. Then D is said to be simply connected domain if and only if whenever D contains a Jordan curve C, it also contains the interior of C. An alternative definition is that D is simply connected if and only if its complement in R2 is a connected set. To have a visual idea, we can say either that D contains no hole, or if J is any Jordan curve lying in D, then J can be shrunk to a point inside D in a continuous fashion. A domain in R2 which is not simply connected is called multiply connected. In the adjacent figure, we have shown a figure which indicates a multiply connected region. Let C1 and C2 be two non-intersecting Jordan curves such that C2 lies in interior of C1. Let R denote the region given by C1 union interior C1 minus interior of C2, where by C1 we mean the trace of the curve C1. Now, we consider two auxiliary curves BF and GE as shown in the adjacent figure. The points B and E are on C1 and FG are on C2. Clearly, the curves ABFAGEA and curve BDEGKFB are Jordan curves. We name the union of their interiors as traces by R1 and R2 respectively. Clearly, R is the union of R1 and R2. Let F equal to Mn be a continuously differentiable vector field on R, then double integral of R of del n del x minus del m del y dx dy. This equals with integral of the same over R1 added with over R2. We apply Green's theorem and hence we get this equals with line integral of m dx plus n dy first over the curve ABFAGEA added with the same over the curve BDEGKFB. So, we expressed it in elaborate form and we find that the integral over BF cancels the integral over FB and integral over GE cancels the integral over EG. So, we are left with integral over the curve EABDE plus integral over the curve FKGKF of m dx plus n dy. So, this equals with integral over C1 m dx plus n dy minus integral over C2 m dx plus n dy. We now study Green's theorem for a multiply connected region. We consider n plus 1 curves which are piecewise smooth Jordan curves. Let them be C, C1, C2 up to Cn. Now, no two of the n plus 1 curves have a common point. We also assume that all the curves C1, C2 up to Cn lies in the interior of C. Thirdly, for every I and j from 1 to n, I and j are distinct, curve C1 lies in the exterior of curve Cj. Then we can consider auxiliary curves as we have shown in the figure. Let R denote the interior of C with interior of C1, C2, Cn being deleted. Let F equal to Mn be a continuously differentiable vector field on an open set containing R. Then double integral over the region R del n del x minus del m del y dx dy equal to line integral over C m dx plus n dy minus summation I equal to 1 to n line integral over C I m dx plus n dy. The proof is similar. We can consider auxiliary curves as we have shown in the picture. So, in this module we studied Green's theorem. We started with proving Green's theorem over simple type of curves and then we studied Green's theorem for doubly and finally multiply connected regions. We conclude here.